Okay, hi guys, and welcome to, well, I guess another live kind of thing, live show, just to help you with some physics. Now my students have got the grade 11 students, they've got a test on Monday, so I thought I'd quickly go through some notes for them. I am you, hey, good to have you here. And now I've kind of changed the style of how I'm going to do this, and what I've done is I've connected my tablet up to my PC, so we shall see how this is going to work. We shall see. Okay, so just with the forces extension stuff and deformation of solids, one thing you need to know, I mean, it starts from GCSE really, is Huck's law. Huck's law states that, well, I've got it down here. Let me just scroll down here a little bit so we can get this thing to work. Come on, die, scroll. Okay, let's see if it's going to come up. Here we go. So, extension is proportional to force for a small distance. This is what the examiners said in 2016 for Cambridge. And then let me scroll back up. Come on. Come on. Is this going to work? Yeah, here we go. Okay. So this relationship you can describe kind of mathematically in that force. Oh no, come on you. Technical problems. Hang on, here we go. Excuse me, people. You know, you practice all day, it's working. Let's try again. Here we go. Come on you. Let me close that. This might help. Getting back to the notes. Okay. Huzzah. Alright, okay, so Huck's law, force in newtons is proportional to extension. And then you've got K here, which is the spring constant, which is in newtons per meter. Okay. Moving on though, that's kind of GCSE. One thing you might need to be aware of is springs in parallel. Okay, so in parallel, if you've got two springs in parallel, okay, well the spring constant of the two adds up. Okay, scroll down. Okay, and then springs in series. All right, it's kind of like resistors. You remember like resistors in parallel? Well, springs in series, it's kind of like the same kind of mathematical relationship. So 1 over kT, the total spring constant, is 1 over k1 plus 1 over k2. And if you think about it, if you have two springs in series, then you're going to get twice the extension, or for twice the extension you need half the spring constant. Next little thing that you guys need to be aware of is, okay, the energy stored in the spring. So the energy stored in the spring, if you've got a force extension graph, the area underneath here is a half Fx. Okay, and so the work done is normally force times distance, but the force is not a constant. So because the force isn't a constant, what you do is you take the average of the forces, and if you think, well, to begin with your force was 0, and at the end it's F, so the average of 0 and F is, well, a half F. Okay, so half f times by x. But we know f equals kx. So if we substitute that in, we get this nice little formula here. Yeah, oh, I've gone too far. A little bit. It's all new, people. New technology. W equals a half kx squared. So this is going to tell you the energy inside a spring. Okay. What's the next thing? Okay, it's going up again. Come on, you. I think next time the problem is the Wi-Fi connection in this room is just not strong enough. Come on. The tablet in front, you see. You see, this is the tablet. It's got all the. I don't know if you guys can see. It's got all the graphics on. There we go. Now what's the change? Go on, back you go. Okay, there we go. Right. Limit of proportionality. Okay, and elastic limit. So, if you've got a force extension graph on a spring, okay, the first little dot, okay, represents the limit of proportionality. So up to that point, the spring is obeying Hooke's law. And then the second little point, that's the elastic limit. So that's when, after that point, the spring will no longer return to its original shape. Alright. Next thing you need to be aware of is stress, which is the force per unit area. It's got this weird kind of little symbol, sigma. And also, okay, strain. So strain is the extension per original length. Okay, next thing. Oh, whoops. Let me go back up. Okay, so what's Young's modulus? It's the stress per strain. Okay. Or a different way of you looking at it, and this is kind of like my favourite little equation here, is Fl, FL over EA. So big capital E, which is Young's modulus, that's equal to the force times the length divided by the extension times the area. These are three different materials and their forced extension graphs. So we've got glass. Glass is a brittle material, so there's just a straight line for the stress strain curve, and then it just fails. Copper is a ductile material, and ductile means it can be drawn out into a wire, and it'll obey Hooke's law up to a point, and then it will start to fail and undergo plastic deformation. And rubber is unusual because it's because it's rubber. You can as you extend it, takes a certain amount of energy, but the energy that it gives back is not enough. Oh, sorry, it's not the same. So the area in that little loop there that you can see, okay, that area is caused by heat loss in the actual rubber itself. Okay, IMU, yeah, you're absolutely right. So the equation, let me go back a few pages. Okay. Oh, where is it? Let me move the microphone a little bit. No, yeah. When I was trying to set this up, it all seemed to work quite nicely, but now this is what happens when you do things live. It fails. Oh no. Yeah. Let me go back. How would a stress strain graph look like for a polymeric material? So something like a plastic. Okay, let me go back and draw it. Okay. No, come on, don't stop. This is mirroring stopped. Oh, sorry, let me get this mirroring going again. Right, we're back. Right, that's how we go. Let's do it like this. So, maybe if I hold it like this, maybe it's going to get a better Wi-Fi signal. Oh man. Let me try and draw it now. Down we go. Come on. So there's your stress. There's your strain. So it's not going to do this. Something like that. It just doesn't really undergo any elastic deformation. It just basically undergoes plastic deformation. Is that what you've seen before for a polymeric material? We'll do something like this. I am you. Are you still there? And like so something like a plastic. Is that what you mean by polymeric material? Natural rubber, amber, wool, silk. Oh, I see what you're saying, yeah. Yeah, okay. Okay, Amy, well, have you got any questions for me? Sorry about the delay, it's slow. Yeah, I'm slow too. It's frustrating. You know, it's technology. Well, it's all an experiment. It's just an experiment. I just want to see, you know, how this is going to work. So yeah, no, I'm sorry too, really. Anyway, have you got any questions for me? Not related to deformation of solids. Guys, just excuse me 1 second. I'll be right back. Someone's at the door. Alright, I'm back. Do you have to memorize such thing as... Oh, hang on 1 second. Hang on. Yeah, hello? What's my name?
Shoes.
Yeah, shoes.
No, come wear them in the car. You already walked outside the garden. Grace gets there before you get there. You know how she's out.
Okay. Bye, guys.
Bye.
Bye. Cheers, John. See you later. Okay. Right, I'm back. Like, would I have to memorize picometer? Yes, that is, you definitely do. Yeah. And also, like, converting as well. So, converting from, like, one to the other. You really do need to know it. Like, let me just get the syllabus up here, okay, and then we can go through it, and I'll show you now. Okay, so we go home, and back again. Okay, I'm just gonna look for the syllabus now, and I'll tell you now. So this is actually running on a 5 megabit upload, so it should be better than it is. Okay, I'm looking at the specification right now. Okay, in fact, let me put it on the screen now. Okay, so this is the syllabus here. It says if you read through it, so it says here, use the following prefixes and their symbols to indicate the decimal multiples and submultiples and multiples of both base and derived units pico, nano, micro, milli, centi, deci, kilo, mega, giga, and tera. Okay, so pico is to the minus 12. Let me make this a bit smaller so you can see me as well. Okay, there we go. I can see what you're saying. So here, yeah, use the following prefixes and their symbols to indicate the decimal sub multiples and multiples of both base and derived units. Pico, nano. So pico is to the minus 12. Nano is to the minus 9. Micro, which has got this unusual symbol mu, is to the minus 6. Milli minus 3. Centi minus 2. Deci minus 1. Kilo is 10 to the 3, mega is 10 to the 6, giga 10 to the 9, and then tera 10 to the 12. So you just really have to just sit down and just go through them yourself. You just need to sit down and learn them, and then how to convert from one to the other, and etc. Okay. Let me just clear this off the screen for now. Okay. What else? Any other questions? What about zeta meters and yoctometers? Definitely not. No, if it's not in the syllabus, they can't ask you really. And I haven't even got a clue. Zeta meter, I bet you know more than me. Yoctometer, what are they? I don't know. You tell me, because I don't know. Yeah, I'd have to look it up. So, no, do you know? Zeta meter, you tell me. I'm going to learn something new now, because I don't know it. I don't know. What about zeta meters or yoctometers? No, I am you. I don't know. Okay, let me. Well, I can just Google it myself, I guess. Yoctometer. Equal to, oh, is it 10 to the minus 24? This is what Wikipedia is telling me. A yoctometer, 10 to the minus 24. Oh, I've never heard of it. What about the other? Zeta meter. Okay, let me Google that one as well. Oh man. Right, connected again. Let me hold it home. Go home. 10 to the 18 and 10 to the minus 16. I really don't know. Zeta meter. What unit is a zeta meter? It's... I don't know. Let me get rid of this because I don't want to start confusing people. The zeta meter, 10 to the 21? Oh, I don't know. I'm you. Whereabouts are you? Whereabouts are you based? What country are you in? I think what I'm going to do is I'm going to get a physical wire from my router to here. Rather than having to use Wi-Fi. This is just killing me. I can't be doing this every week, just having it so laggy. In the East Midlands. Oh, UK, England. Okay, yeah. I mean, I live in South Africa now, but I used to live in. I mean, I am originally from England. I mean, I was born in England, and I mean, I teach in South Africa now. Let's move this back a bit. Any other problems or anything you want to talk about, or physics related, or anything you're not sure about? Are you doing AS or A-level? I wonder if I type it'll be faster. And also, what's the exam board? Is it is it Cambridge or? Okay, guys. Anyone else here? I'm going to start A2 in this September. Okay. I think I prefer teaching the A2 than the AS level. It's really interesting. Like especially things like the photoelectric effect, and starting to do like some quantum mechanics, EdXL physics, OCR maths, and AQA chemistry. That's an odd mix of exam boards. you know, to be doing all different. I mean, maybe that's just the way your school's doing. No, but that's unusual. You know, to have just but I guess that's just up to the school you're at, I guess. Live physics. What's going on with the stream now? Yeah, the A2 stuff. The A2 stuff looks much more fascinating. Yeah, no, it really is. Like it's hang on 1 second. Guys, you're not streaming anything, are you? Hang on, let me. I've got. Oh, hang on, let me get the book. Let me show you some of my. I hate electricity. I don't understand potential dividers. Okay, well let me help you with that. Okay, so potential dividers is not that bad. Okay, but let me try and explain it. Okay, let me go on a new page. Okay, so in a potential divider circuit, you've got something like a. Oops, let me draw a better cell. You got something like this. But let me pick this up. Come on, you. Let's call this. Okay, sorry, that's a bit rubbish, but let's call this R1. Let's call that R2. Okay. So we've got current going around here like that. Now, because it's basically a series circuit, okay, the current is the same everywhere. Okay, so the current going through R1, R2 is the same everywhere. Okay, I'm just going to give this a voltage. Oh, let me go for a red. Okay, so let's call that. Okay, so V. So we're going to call that V in. So that's the voltage going into the circuit. Now let's say you want to know the potential difference across R1. Okay, so do this. Okay, so there's my my voltmeter. Okay, so I'm going to call that. Let me move this down a little bit so you can see me A little bit better. Okay, so I'm going to call that, and I hope you can hear me okay, I'm going to call that my V out. Okay, this is working a lot better actually, because I think the computer's Wi-Fi and the tablet's Wi-Fi are probably messing each other up. Okay, so the total resistance, so I can see R total is equal to R1 plus R2. Okay. Now let's just go back to generally. V equals IR. Okay, so V equals IR. So we can say V in, come on tablet, oops, stop being laggy. So V in is equal to I times, well, the total resistance, so it's R1 plus R2. Okay, now let's just go back here, and we want to know, well, we know the current is the same everywhere. Okay, so the voltage V out is equal to I, go over here, times R1. No, come on you. It was... okay, so there's our circuit. So we've got V in is equal to I times the total current, and then times R1 plus R2, and V out equals I times R1. Now with these two equations, I'm just going to rewrite them in terms of in terms of I. I'm going to make I the subject. Okay. I hope you can still hear me, but I'm going to make. I'm just going to double check the audio. Yeah, I'm going to make I the subject for both of these. So for the first one, equals I. Okay, but that's also, I can say V out over R1. Come on tablet, get that Wi-Fi. Okay, so these two things are equal to each other. So V in R1 plus R2 is equal to I, and I is also equal to V out over R1. Okay, the final little part, okay, what I'm going to do is move, if you see you've got R1, put R1 here, like that. And if I just tidy it all up, I get V in times by R1 over R1 plus R2 equals V out. And that's it. Okay, so let me just go through that again. So from the top. So we've got our circuit. Come on. Okay. So we've got our circuit here, and we said, well, we've got two resistors, R1 and R2. We're going to say V in is the potential difference going into our circuit, maybe a cell or something like that. And then we've got V out, which is the voltage across R1. Okay. What's the total resistance? Well, the total resistance is R1 plus R2. So what we can say is, going down, okay, the general formula is V equals IR. Okay. So with our general formula, what I'm doing is I'm saying, well, V in it equals I times the total resistance R1 plus R2. Okay, that's just looking at the circuit as a whole. Then we say V out equals I R1. So then we just make them both equal to I. So we make I the subject. So V in over R1 plus R2 equals I, but I is equal to V out over R1. Okay. Going down. Okay. V in equals, okay, then what I've done is I've moved R1 over to the other side. So then I get V in, okay, times R1 over R1 plus R2 equals V out. Okay, joined by Ghost 1808. Could you please explain double slit interference? Okay, well, I will try. Okay, IMU. How was that? I hope, does that make any more sense for potential dividers? I hope so. Okay, Ghost 1808. Okay, double slits. So Young's double slit. So so you got two slits here. You got some kind of maybe you got a laser here or something. No, it's laser with an S. Oh, come on, laser. Okay. So you got a laser or something. Okay. So what happens is the laser light can go through the slits here. So I've got my screen here. Okay, so what happens is the laser light goes through here. What's a good colour for laser light? Maybe, so you're going to find your orange laser light here, and then through the gaps here, the waves are going to go through like that. Something like that. Okay. Now, what you would see on the screen is where the path difference between the two slits is a whole wavelength, you'll get lines of light. So then, normally there's one in right there, you'll get a line and a line, a line like this. So, I'm just going to get rid of the mess in the middle. See, now the tablet's been here. Okay. Now, what you need to think about is this: the distance between the slits here. So you've got a beam of light coming from here, beam of light coming from here. Now the first one, this is easy because the difference in the lengths for the very middle one, the difference in these lengths is 0. Okay, so the waves as they come in, the wavelength, the phase of the two waves as they come in here, they match up, and then you get a bright fringe. It's the same for the next one here. So let me try. Let me go for one up here. Okay, so like here as well. So that distance there, light's coming from there and going from there. So 1, 2, 3. The difference again in these two lines, the difference in length, okay, will be equal to a number of wavelengths. In that case, it'll be 3. Okay, let me just put some of the maths in here. So this is D, distance here. Between these fringes, we call it X. This here, the distance between the two slits is A. And let me just say this has got a wavelength lambda. I'm fine. Thanks. No, I'm fine. Thank you. Okay, you can put it. I'll take it in a bit. Thanks. Okay, so the equation, okay, for this is lambda equals A x over D, like that. Okay, can we do some problems on potential dividers after ghost problem? Okay, sure. On potential. Okay, why not? Okay. Ghost. This is the equation. So if you double the distance between the slits will double. Obviously, because the waves are moving further apart. Is this what you? Is this what you're after, Ghost, or is there any particular problem based on this? But this is what's happening really with the double slits. This is the equation that you need to know. So lambda ax over d, and then IMU. Yeah, well, I'll just go through like one example. Well, I'll just make up a problem. Be easy. It's not a big deal. Okay, well, I've not heard from Mr. Ghost, so IMU. I'll invent a problem. Okay, so here we go. Okay, so going back to potential dividers. I'm getting back here. Come on. Come on, Wi-Fi. Okay, here we go. Okay, so we said, okay, the equation is V out is equal to R1 over R1 plus R2 times V in. Okay. Okay, so let's just say we have got 12 volts here. Let's say this is 4 ohms, and then what's a nice value? 8 ohms. Okay. So if you want to know the do this. Okay, so let's say we want to know what's the voltage across our potential dividers here. Come on, man, lag, mega lag, mega lag. Okay, so what I would do is, if I want to know what the voltage out would be, okay, so in my equation, I'm going to do, well, R1, which happens to be 4. Okay, so 4 divided by brackets plus 8, and then times that by 12. Well, I've kind of been a bit sneaky here because I know this is going to work. The actual answer in this case is going to be 4 volts. Okay, so there'll be 4 volts across my 4 ohm resistor. Okay, let's say if I wanted to know what's the voltage across the 8 ohm, then instead of having 4 at the top, okay, oh, let's give it why is this thing so big? It's my daughter's been playing with the tablet, that's why. Changing it all, okay. Then that would be 8 if you want to know, well, what's the voltage here? It'll be 8 over 4, and then find out to be 8, like that. Okay, it is. I hope that's explaining it. Is that any clearer? Just what you have to do, you know, just putting in the stuff in the equation. All good? It's not that bad, I guess, the lag. Lag. Okay, ghost. Going back to ghost problem. Would we be